Hey guys, welcome in this new sudden video. I was working and preparing a new tutorial for you guys about the DC-DC converter, where we will use a digital potentiometer to control the V out of the DC-DC converter. However, suddenly I have found some interesting things to make a new tutorial about, or how to control the potentiometer. So here we have two potentiometers, both of them from microchip. Okay, they are MCP4141, this on the left, which is a single potentiometer, and the one on the right is 4241, which is a double or dual potentiometers. Both of them 100K, but there are some difference between these two, which we can directly control them using an Arduino hardware SPI. Because this potentiometer got only a single line or single pin that control the read and write to and from the master. However, this one has two pins, one for the read, one for the write, or one for in, one for out, which is the master in slave out and master out slave in. However, this one is only pin and we need to multiplex it, so we need to see how to control these potentiometers, how to set the values, and then we will continue with the DC converter tutorial. Without further ado, let's get started with this new tutorial. Well, so enough talking about the MCP4241 potentiometer. Now let's move on to the single potentiometer. Okay, the single digital potentiometer. The characteristics exactly same like the first one, which is the dual one. All the features are same, except that it share same pin for the CL data in and CL data out. So it will be multiplex that pin to send and receive data from and to the host or to the master. Okay, compared to the first one that we work on, which is got separated data, which is the serial data in on pin number 3 and serial data out on pin number 13. So these two makes our life easy. However, in this chip got a multiplexed line. So here is what make it a bit complicated and not same as the first one. The rest are all same, exactly same, not much different. And also the other difference between the first and the second one is if we go to the memory addresses table, it should be somewhere here. Yep, here we go. So the memory address will be exactly the same, except there will be no wiper 1. So will be only wiper 0 because it's a single resistor. So will be volatile wiper 0 only, and non-volatile wiper 0. So volatile wiper 1, non-volatile wiper 1 will not be accessible this time because we don't have it as simple as that. The rest should be the same. And now if we go to the wiring, here we go. So the datasheet suggested to do the following. If let's say we have a separated data, we just connect it same like what we did at the early stage of this video. However, if we have a multiplex this data, which is what we have now on 4141, so we need to add a resistor. Then we send it to the host as SDO. Then we take another pin or another wire before the resistor near to the chipset and set to SDI. Okay. However, this one, if we need to read and write, okay, because we need to read and write from the chipset. However, if we need only to write, only to control the potentiometer without feedback, without reading the data from it, so we can just directly connect it to the let's say to the SDO CL data out from the host to the chip without needing a resistor, without needing another connection. And here, if the host is supporting the what they call multiplex on the single data, so we can connect directly without any resistors. Okay, so this is the connections. However, due to the fact that the Arduino doesn't support the multiplexing on the same pin, and also we can use this, we cannot use this method by putting a simple resistor on the way of the SDO and SDI, because again, the Arduino, the hardware of the Atmel chipset that we are using, it will set always the SDO as output and the SDI as input, so it won't be multiplex among them, and it will never drive the target, the digital board in the digital potentiometer in this method. So yeah, there is no way of using the Arduino in this, the hardware SPI of the Arduino in this case. So we need to use the Bit-Bang, okay, and we simulate the multiplex of the I/O on the same pin, and this is what we are going to do. And here is the wiring that we will follow. So again, here is the MCP, okay, pin out, and again it should be in a U shape, but here I put it like in line to make it easier, but it's just like in shape, and it will be like a U shape. So we just follow the pins of the MCP will do. So the pin number 1 will go to the chip select Arduino pin number 10. Number 2 will go to the clock, and I guess let me open this so we can follow on. Okay, so where is it? Here we go. Okay, so pin number 1, the chip select, will go to pin number 10. The clock will go to 13. Pin number 3, which is the multiplex SDIO, will go to pin number 11, which is no more actually MOSI. It will act as a normal IO, okay, with the Bit-Bang method. So 4 and 5 will go to the ground, okay, because we want to have a voltage divider on the resistor here. Pin number 6, the wiper, will go to the multimeter so we can measure the output. Pin number 7 and 8 will go to 5 volts. Okay, so this is the wiring that we will follow in this chip. Okay, guys, so enough talking about the data sheet, and let's dive into the coding. So here is the IOs, the wiring that we need to follow, same as we discussed previously. And here is the command, how can I say, command string that we need to construct, which is exactly, again, same like the previous chipset. And here we have the memory address that we can access to either read, write, or increment, decrement, etc., which is exactly the same. Again, however, we can't access these because we have only one potentiometer, so we will have only potential 0. So we can't access the volatile wiper 1 and non-volatile wiper 1. So these two are not valid in this case. The rest of the command type are exactly the same: read, write, command increment, and command decrement. Okay, so what here we have, and if you notice, guys, we don't declare any SPI hardware library because this case we are not using SPI hardware. We are using the Bit-Bang to simulate the single multiplexed SDIO line. Okay. So here are our pins. We have the chip select number 10 and also clock 13 and SDIO on pin number 11. And if you notice, we have only one pin, which is number 11, that's responsible to read and write data to and from the chipset. Okay, so here I have adapted the same build command function that it's helped me to build the command where we will have the memory shifted by 4 and we edit with the command type shift by 2 to give space to the data. So this is exactly the same what we discussed previously. So this is the first new function that it's responsible to write a bit into the chipset. Okay, this to Bit-Bang write a chip. So this is a common way when we do a Bit-Bang for the SPI or any other protocols to make sure that we convert any data coming or any, like, for sure bit, it should be 1 or zeros. We check the bit. If it's 1, we send to high. If it's 0 or otherwise, we'll be setting low. We set to the SDIO. Okay, and then we need to cycle the clock. We cycle the clock high, clock low, and give 1 microsecond. This is following the datasheet requirements. Okay, and here is to read 1 bit. Okay, these are the very how can I say, the construction functions that we use later in all the rest of the code, where we will be write bit or read a bit. Okay, so to read a bit, first we need to bring the clock high. Okay, then we will read the data from the SDIO pin, which is pin number 11 here. Then we bring the clock low again. So just like give 1 cycle, and between the cycles we will read 1 bit. Then at the same time we will return this bit to the callout whenever we call it. And if you notice here for the write, we need to have 1 parameter, which is bit, that we were responsible to write it to the destination. And here is the SPI write byte. Okay, so the byte actually just like we need to call 8 bits to be written. So if you notice here, when I write byte, first I need to set my SDIO as output. Okay, so if you notice here, when I'm doing writing, I'm not setting any output. I mean, I'm not changing the mode of the SDIO pin, because I won't write only a single bit. I will at least write a byte, or a register, which is the register in turn will write a byte. Write a byte, then the byte will write the bits. So at least I will write a byte, and here I'm changing the mode to the output, so I can multiplex. That's why we have multiplex. So when we write byte, so we need to change to output, and later we have read. So the read we need to change to input pull up. Yep, exactly. Okay, so since I have write, so I will change the pin mode of the SDIO to output, because I want to output data. Then I need to call the bit or write bit 7 times. I have counter from 7 until 1 until 0. Okay, and I need to send my data, which is the 8 bits. Okay, so I send my data, I shift them every time. I shift them by 1, or actually not by 1, because I'll start with 7, then I'll shift in by 1 by 1. So this one I will get the data in sequence. For example, so here I have 0B 101010, etc. So when I got the 7, so it's mean I will get only the first bit to be sent. Then the next cycle will be 6, so 6 I will get the next bit, and etc. and so on. So I will write bit by bit, okay, to the destination. And for the read is opposite to the write. And if you can see here again, we set the pin mode of the SDIO to input this time, and we set it as a pull up. And we do exactly the same. However, this time we will read bit, okay, and we store it in the value that we declared up there. So the value, we will compare it or we add it to the data coming, and whenever we receive data, we will shift it again to the left by the value of the loop, and we will accumulate it in the value variable. And this one actually, guys, if it looks hard for you, you just assume this one, or imagine it is same like if you have this instruction like I plus equal to, let's say, 1. Okay, exactly the same. but here will be value or equal to this data that's coming, and we are shifting it. Okay, something like this. Then we return the value that we accumulated, which is the 8 bits again. And here we have write registers. So register write, again, it might be more than 1 byte, definitely is 2 bytes. And when we write a register, we need address and we need data to be written. Okay, so here, since we start to write now directly to the destination, so we need to bring the chipset low. Okay, so bring the chipset low to activate the target, and then I will build the command. Okay, I build the command based on the address, and because since here again is a write, so the write will be command write. So I build my command following the address, the memory address I'm targeting it, and write command. Then I send it to my target. Then I will send my data. With this, I have completed written my data. Then I bring the chipset high again to isolate the target. Okay. And here is the step. So step will be responsible for increment decrement process, which is again need address and type. So type here will be decide whether it's increment decrement, as we will see later in the caller. So the address again is the memory address that we're targeting, which mostly will be the non-volatile wiper potential 0. Again, I will set the chipset to low. I give some time to settle down. Then I will check the type. If the type is equal to increment, so the command will be increment. The command here will be increment command. Otherwise, will be decrement. Then again, I will build my command using the address and the command that's been decided here, following the strings that's been sent by the caller. Again, digital write high. So I will isolate my my target. And here is the read register. So the read register will be again same like the writing register. However, this time I will return the data from the target. So I will build the command here. Actually, I can put this one in the command here, but this one, again, is just another way to do it. So since we have a read command, so I will put the read command here. I will build my command string following my address, the target address, and also the command read, because anyway, I want to do read. Then I'm bringing low the chip select, preparing the chip to receive my instruction. Then I have the bin mode to be output, because I'm outputting data first. Okay, because you see, when I'm reading register, first I need to send instruction, so I need to have output on my bin first, send. Then when I'm receiving, I need to convert it back to input. Okay, so when I'm sending my command that I need to read from this address, I need to assign the SDIO to output first. Okay, after I send the command, then immediately because I will expect the chip to return back the data on the same pin, so I will switch back the pin into the input with pull up. Then I will read my data, so the value will be reading bit from that pin, which is the SDIO. Okay, so here is the 3 key things, guys, you need to remember. When we are reading registers, we are not directly or immediately read. We need to send the command that asking the chip to send me data. And when I'm sending command, I need to set my SDIO to output, because I'm sending to the chip. Then when the chip starts to send to me, I need to immediately change my pin to input, so I can start receiving and observing the data. Then I collect the data using the read byte. And at the end, I just set the chipset to high and returning the value for sure to the caller. And here is the setup function. Again, serial is been enabled or begin with 9600 baud rate. The pin mode for the clock, for chip select and clock, they're both output. They won't be changed. They're always fixed. Then I have set the chip select to high, because at the initial stage of the code should be isolated. I shouldn't talk to it immediately until I finish initialize my data. So it will be set high first, and the clock is start with low H. And here just print like, okay, I Bit-Bang the SDIO SPI test. Then I give some delay. So with these guys, these are all the important functions I have declared and I will be used. So later we just need to start to do some testing, like we start to send data to the wiper or read data from T-crons and play with the EEPROMs or whatever. Okay guys, so let's continue. You can see here I have replaced the dual resistor, dual potentiometer with a single potentiometer, the smaller one, the MCP4141, and I wire it up using the same wiring diagram I showed you earlier in this tutorial. Okay, and again I'm using the multimeter to measure the wiper, which is presenting a voltage divider between the ground and 5 volts from the Arduino. Okay, so now I will continue from here. So the first thing I will check is the wiper zero. Is the wiper zero write data? So what I will do here, I will construct a loop again. Or let me copy paste maybe. So okay, we do it for. So for we have integer I equal to 0, and our I is less than 1 to 9, and I plus plus. So this is our loop. What we will do here, I will print first. So serial print line. We print the I, so we know what is the value being assigned to the registers or to the wipers. Then what I will do, I will write to the register. Okay, so which register I will write to is the volatile wiper underscore wiper. Put 0, put 1 is not exist here because it's a single potentiometer. Then I will send I, and that's it. That's it. Then I will add a delay, so we can read it using the multimeter. I will add like 250 again. Okay, this is to go up, I mean from 0 to 128. Then the other loop is to go down or count down, and here I will add delay again of 250 milliseconds should be okay. And here also I will add a delay of 250 milliseconds as well. Then here will be the other way go down, so we'll start from 1 to 8, and the I is more than or equal 0, and I minus. Okay, that's it. So let's compile and send to the target and see how it's behaved. Okay, it's compiling and uploading. That's good. So let me open the CL monitor to see the behavior. There we go. It's sending. Yep, sending the data, and you can see here, guys, it's counting down. Actually, it's counting down, although we are going up here, but it's just because of the ground and VCC is flipped. So if we flip it, then it will be the other way. But anyway, it's working as intended. So now if we wait it will go down until 0, then it will go up again to 5 volts. Okay. There we go, it's 0 when it's 128, then it will go up again when the value is dropped to, the counter we send drop to 0. Okay guys, so what next we can test here? Let's test the increment wiper, or the wiper increment and decrement. So from here, instead of we write to a register, I will comment this guy. So we will send the second function that we developed, which is the step. Okay, so the MCP step, yes, we need address. Address is our volatile wiper 0. And what we send here, we need a string of, let's say, increment here for sure, because we want to go up first. And then at the second one, at the second loop, We will perform what, guys? Can you guess it? Decrement. Yep, that's it. So now we can hit upload and see the behavior of our chip. Oh, we got something wrong. Yep, sorry, I forgot. Semicolon here, and upload. Okay. Okay, cool. So it's uploaded, and we can see CL monitor. Yep. See now, CL monitor is counting up, and we are increasing or decreasing. Oh yeah, again, because the VCC and account has been flipped, so that's why we can see something like this. And again, we can see it's the same behavior we have noticed when it's go more than, let's say, 128, because of the previous value has been already stored there. So whenever it keep increasing or decreasing, the value is maintained. So now when it reaches to 128 only, will be go back to the normal operation. So this behavior is expected and is normal. Okay, 128 now should go up again, is good, and yep, I'm happy with this result. So what next? So okay, we have done the write, we have done increment, decrement also done. So let's go to read the data from the volatile wiper. So to do so, I will comment all these guys. We don't need this. Then I will just read it on the serial. On the sorry, read it on the for sure, read it on the serial, but I mean I will perform the code change on the setup because I want to read it only once, no need to continue reading it using the loop. So here we will read the volatile wiper 0. Okay, how to do so? I will print first. I will print that. Let me print. Oh, sorry. Let's leave it. Print line. We use this as a separator. Then I will print some message to show us that the volatile. Where is it? This guy here. So the volatile wiper 0 is equal to this. Then I will serial print. Oh, sorry. So serial print line what? I will print the read register function. Then it's need a register value or the memory address. I want to read the memory address of this. Okay, so I believe that's it. So let's hit upload and see what is the result, the current result that's been stopped on. Okay, it's uploading and cool, done. Let's see. Now we should see a single value 133. Yep, exactly. So this is the current value 133. And again, this is the volatile, guys. This is the volatile. So if I repower the chip, this one will go to the volatile that's been already saved inside the chip. So if I take out the power and put back again, now we should see the wiper go to 64. Yep, exactly what we expected. So now if we change the wiper using the write register, let's say here I'm writing, let's say 1, 2, 3 and upload. Now we should see that the wiper, the volatile memory for the wiper, it should set to 1, 2, 3 now, and even our data should go down. Yep, 1, 2, 3. Here we go. Okay, guys. So now let's read the non-volatile. Let me copy this. So to read the non-volatile, I will copy this. Exactly, actually, is the same. The change is we'll need to call the non-volatile. Non-volatile. Is it non-volatile? How did we declare it? volatile, non-volatile 0 is NV. Okay, so just need to call this guy. Where is it? Where is it? So this one should be non-volatile and this one non-volatile. So now we should have the non-volatile value with us. So the non-volatile, guys, again, if you remember, we should have 64, although the volatile has been updated. And now since we haven't power up or recycled the chipset, so the volatile should maintain at 1, 2, 3. Here we go. See, the volatile maintain at 1, 2, 3 because we haven't powered up the chip, and the volatile is sorry, the non-volatile is 64. But now if I power up or recycle it, now both of them should return 64, and our reading from the multimeter is go back to 2.5 or 2.5 actually. Okay, cool. So now if I want to change the volatile, change the non-volatile, so exactly same what we did with the volatile, we just need to change the register or the memory address to the non-volatile. There we go. So the non-volatile now, it will be set to 1, 2, 3, for example, or maybe I can set it to 10. Although if you remember, now it's set to 64. Now it should be updated to 10. Okay, good. Now we should see that the volatile, it maintains 64 because this is the last value being recorded in the volatile. Okay, and the new non-volatile is changed to 10 because we just updated. Okay, so now if I recycle the power for the chip, both of them should go to what? What do you expect? Expect what, guys? Both of them should go to 10. Should be, yes, both of them 10, because when we recycle the power, the non-volatile will be override the volatile. Okay, and you see even the multimeter show 4.7 volts. Okay, cool. So let me comment this. We don't want to overwrite it again. So next, what we can test. So we finish with the volatile, sorry, non-volatile done, volatile done. This one we read and write already. Now we come to the T-con. So let me add a delay here of 250 also should be okay. So now I will work with the T-con register. Let's print the T-con first. So I will call this, which is again is the same function we will call. It's read register, but this time we need to call the T-con memory address. Okay, so the T-con is here, and let's see the results. Okay, and here we go. So 255. By the way, I don't want to see it like this. I want to display it as a binary again. So here should be a binary. Let's upload again. Okay, so now I can see my ones here, which is exactly matches the data sheet that we discussed earlier. So now if I want to update my T-con, again, I can use the write register here. Then I will assign my T-con as the address I want to go to do the write or perform the write. Then I will send the data that I want to be changed. So 0B, because it's binary, 1, 2, 3, 4, 5, 6, 7, 8 bits. So now what I want to do, for example, I want to change the R0B. Okay, the B terminal of R0, which is the first one. So if I set this to 0, but before that, let's set this, before we write this actually, because this one might affect the reading. So let's set this one back to 64, because now our this wiper is not in the middle. If we put 64, so we can see the difference actually more obvious. So we set this to 64 first. Okay. And then we continue with the T-con. Okay, let me activate the multimeter and see if everything good. So I'll power my chip. And yep, it's 24255. Okay, good. So now I will write into my T-con and I disable B. Okay, let me copy and paste this. This one is from the previous example. So I will disable this one as 0B terminal. That's why I set it to 0. So now let's see the effect on the chip. There we go. So terminal B is being connected to the VCC. Okay, so when I disconnected it, so the reading will directly take the signal or the reading from the ground. So that's why we can see 0 volt on the multimeter. So now if I disconnect the A, so if A is 0 and I connect back the B, so now what is the multimeter reading will be, let's see. Yeah, I guess you guys, you know what is the reading should be, because we disconnect the ground now and connect it directly to the 5 volt of the VCC, and here we go, we can see a 5 volt. And again, this thing is just volatile. So if we don't write anything to it, we just keep it as it is. First, it will maintain as a 5 volt because it's a volatile and still there, but we haven't recycled the power. So once we recycle the power, all the T-con previous settings will be reset back to the original. And here we go, 255, and the T-con go back to normal. Okay, done with the T-con. Now let's go to the status register. Again, status register exactly same, not that different. We can just change our memory register, which is the status register. So here is our status register and status register binary. Yep. Okay, let's see. Okay, good. So let's find out. Here we go, our status register, which we expect at the MSP 3 bits will be all ones and the rest are all zeros, which is exactly match our data sheet and also the reading that we got from the first part of the video where we work with the dual potentiometers. Okay, so status done. Now what we left over with the EEPROMs. Okay, cool. Almost there, guys. So thanks for watching. So let's continue with the EEPROM. EEPROM, so let me put another separator here. Okay, so for the EEPROM, I will use a for loop again. Let me use the same for loop here. So for integer address equal to not 0, but we assign it to the first underscore address of EEPROM, yes. And I, it will be, or not I, we change to address, is less or equal than the last address of EEPROM. Then our address will be ++. Okay. So what I will print first, let me have a serial print. So serial print, first I will have the message EEPROM of 0x. I don't want this guy here. And close. Then I will print the address, serial print the address. Okay, I want it to be in hexadecimal. Okay, cool. Then I will close my statement by add on close the bracket and equal to. Then CL print line, I will bring the data. So since we need the data, I mean we need to read from the register. Read from the register, and the address is the address we assign here, which is the address. Okay, I believe that's it. So, oh, sorry, some colon, and yep, let's go and see the output. So this one should return or should read all the current saved data inside our EEPROM. Okay. Okay, here we go. So this is our EEPROM. We have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 bytes of EEPROM, and this is the data that is populated with. So now if I do any changes, let's say here I will perform some changes. How to perform changes? Again, we do register write. This is read register. We copy the write register. Here we go. So I will perform maybe like 2, 3 places. Okay, and 3 places following the, let's say, first 3. First 3, 1, 2, 3. So the first one and the second one will be the first plus 1, and the next will be plus 2. Okay, so the first one I will put like 10. The second one is 20. 20, no, 22 anyway, and the other one will be, the third one will be 30. So if we notice here, guys, the first one is 10, the second one is 1, 2, 3, the third one is 24. But now I will update them with these values, and it's good to have a delay. Okay, delay here of, let's say, 500. Give time to the EEPROM to digest our data we send to it. So delay of 500. And at the end also we give some delay. Okay, guys, so let's hit upload and we see our data here. Here we go. So if you see, guys, this is the old readings, and these are the new reading. We have 10, 20, 30, which is exactly what we updated here. That's cool. That's cool, guys. I guess we have almost reached to the end of the video. Yep, nothing else to be done. Yep, that's it. That's it, guys. Finally, we have reached to the end of this tutorial. I believe it's kind of lengthy also video. So again, just to recap, guys, the main purpose of this video the main purpose of this video actually is to show you how to work with the multiplexed data, okay? Especially if we are using this chipset, which is 4141, that use the SDIO, that use a single signal for read and write. We can't use the Arduino SPI hardware. We need to write our own Bit-Bang SPI code to communicate with it. And this is the struggle or the challenge I was facing when I'm working with this chipset, when I need to use it to control my DC-DC converter. Actually, I was planning to work with a DC-DC converter, but when I faced this issue, then I thought that, okay, you need to know about this one first, then we continue with the DC-DC converter. Because later on, we will use the exactly same code to control the resistor, the digital potentiometers. Then the digital potentiometer, it turns to control the DC-DC converter. Okay, so here we have learned two things: the direct or the straightforward hardware SPI coding, where we talk to the dual potentiometer, and then we develop the Bit-Bang code, okay, to read, write register, read, write byte, and read, write bits, and also how to construct the command. So all this we have discussed in this tutorial. And yep, I guess now, guys, we are ready to go forward and work with the DC-DC converter in the next tutorial. So I hope you have learned something new, and see you in the next tutorial.